Hey there, beautiful people. In this video, we're going to look at LeChatelier's principle and equilibrium in general. Now, this is going to take a non-mathematical view of LeChatelier's principle and equilibrium. So let's jump right into it. So up until this point, we've assumed that all chemical reactions move in one direction, from the reactants on the left to the products on the right. However, there's a lot of reactions that occur in both directions, meaning that you have reactants turning into products and products turning into into reactants. Those are called reversible reactions. Now, when that reversible reaction is exactly going in the opposite direction at exactly the same rate, then you have what's called equilibrium. That means you have the same amount of reactant turning into product as you have product turning into reactant. Picture it like two people throwing a ball back and forth. Okay? When one person's throwing the ball, it's going in one direction. When the other person catches it and then throws it back, it's going in the opposite direction. That's reversible. Now imagine both people have one ball each. If they both throw the ball at the exact same time, the ball will travel by each other in the air and you will have equilibrium. One ball going in each direction at the exact same time. Now understand that it's occurring at the same rate. It doesn't have to be the exact same amount, it just has to occur at the same rate. So for example, one person could be throwing from a bucket that has a lot of balls, and another person could be throwing from a bucket that has very few balls. As long as they're throwing at the same rate, it doesn't matter. One person might be throwing two at a time, one person might be throwing one at a time. Now, in terms of equilibrium, we can exert a stress on the equilibrium reaction and cause it to shift, meaning it might make more reactant or it might make more product. There are four types of stresses, and this is LeChatelier's principle. LeChatelier's principle says an equilibrium system under stress will shift to absorb the effects of that stress. There are four stresses. We're only really going to deal with three of them, but I'm going to talk about all four. I'm going to give you all four here. Number one, change in concentration. Number two, change in pressure and volume. That will only impact gases, and I'll talk about that in a minute. Number three, change in temperature. Heat it, cool it down, take away heat. Or lastly, add a catalyst. So we're not going to talk about catalysts in this video. We're going to do that in later when we talk about reaction speeds. Okay, so let's talk about concentration first. Now, concentration impacts all reactions, all equilibrium reactions, because you can change the amount of a substance. So what we're going to do is, think of it like a seesaw effect, okay? Where the double arrow, see the double arrow now? The double arrow is the middle of the seesaw. N2 and H2 are on the left, and H3 is on the right. When we add more stuff on the left, it will automatically shift to start making more product, okay? So this is what's called shifts to the right. So if we have more of what's N2 or H2, we'll start producing more NH3. The reverse is also true. If we add more NH3, we'll start making more H2 and N2 to use up the extra. And the key is, the reason we're doing this and to make it shift is to use up the stress that we just did. So think about it in terms of your life. When you have stress in your life, whatever that stress is, you do something in your life to absorb that stress. So let's say all of a sudden you have a huge project dumped in front of you. What would you do? Well, maybe you sleep more to reduce the stress. Maybe you buckle down and work more. Maybe you stop watching TV so you can get your project done. Maybe you have more anxiety and stress, so you start fighting with your parents. Whatever it happens to be to absorb that stress, that's what you're going to do to maintain your equilibrium. Once that stress is gone, once that project is gone, then everything kind of goes back to normal. Now, if you remove a substance, then it goes back to that side. Okay, so everything shifts towards that side. So if I remove N2, the reaction will shift towards N2. If I remove NH3, it'll shift towards NH3. So adding reactant always shifts to the right. Adding product always shifts to the left. But if you remove, then it always moves to the side you removed from. Now let's talk about change in pressure and volume. This impacts gases only. So let's look at a reaction that involves gases. How do I know it's a gas? Simple. I can see these little G's all the way through the reaction. Obviously, if it was an S or an L, it would be solid or liquid. And if I see a Q, again, it's going to be aqueous, means dissolved in water. Okay? So for changes in pressure and volume, it does not impact solids or liquids or aqueous at all. We're only looking at gases. Let's take a look at gases. In order for reactions to occur, molecules must collide. So let's look at gases bouncing around in a container. So I have a container here, and I'm going to pump in some gases. And what I want you to notice as these gases are moving around, they're going to start flying around and they'll move all over the place. I want you to notice the number of times they bump into each other. I don't care if they bump into the wall. I want you to start looking at the number of times they bump into each other. So you can see every time these two things bump, there's going to be a reaction. That's what we're going to assume. So notice that molecules are moving around and they have to bump into each other. This is what's called collision theory. Collision theory means that molecules must collide in order to react. Now, we can alter how that happens. Okay, so let's run through and then I'll show you through the examples. Let's talk about the increasing pressure. If I increase the pressure, okay, I'm going to increase the collisions that these gas molecules are going to be under. The reaction will shift to the side with a fewer number of moles. So I have to look at my chemical reaction. I can see on this reaction I have 1 mole of N2, 3 moles of H2 on the left. That's 4 moles. On the right, I only have 2 moles of NH3. Therefore, if I increase the pressure, I will increase the number of collisions. The reaction will shift to reduce the number of collisions. Therefore, the reaction will shift to the right to reduce down the number of collisions. So in this case, my NH3 will go up and my N2 and H2 will go down. If I increase my volume, I will decrease the collisions, and by default, the reaction will shift to the side with more moles because I need to increase my collisions back up. So if I increase my volume, my reaction, because this side has 4 and this side has 2, my reaction will shift to the left, making more N2 and H2, and it will decrease the amount of NH3. Now let's see that in play. Now pressure and volume are connected to each other. You're going to see that in a second. So if I increase my volume, I make this bigger. Watch what happens to the number of collisions. The number of collisions between molecules goes way down. Okay? You will also notice that the pressure goes down. So when I increase my volume, my pressure goes down. So remember, let's jump back. Increasing volume decreases collisions. My reaction will shift to the side with more moles. So in this case, this reaction would shift towards N2 and H2. So when I increase my volume, notice what happened. The collisions go way down. Now, let's go in the opposite direction. If I decrease my volume, watch what happens to my pressure. My pressure shoots way up. Notice the number of collisions. The number of collisions between the molecules goes way up. So since the molecule collisions go way up, as I go back to my presentation, my reaction will shift to the side with fewer moles, which would be the NH3 side, increasing this side and decreasing this to keep the number of collisions at the same level. Keep in mind with gases, the number of collisions is what our stress is. So when I decrease the volume, I am increasing the number of collisions. When I increase the volume, I am decreasing the number of collisions. So we have to increase the moles to get my collisions up, or I have to decrease my moles to keep my collisions up. Okay, now let's talk about the effects of temperature. Let's look at this chemical reaction. Again, it doesn't really matter whether it's solid, liquid, or gas in this because it's going to kind of generally go by the same principle. But mostly we're going to talk about this in terms of aqueous and in terms of gases. So if the reaction is exothermic, so we have to go back to our thermochemistry and remember exo and endothermic. Remember that exothermic means heat comes out, it exits. Endothermic means our heat goes in. So if it's exothermic, we're going to think of heat as if it's a product. Okay? So we'll have reactants, products, and then the heat is going to be on the product side. Once the heat is on the product side, we're going to treat the heat like we're talking about changing concentration. So treat heat like a changing product. If we increase the heat, the reaction would shift to the left. So if we make an exothermic reaction hotter, so we add heat to an exothermic reaction, something that's giving off heat, then we'll actually decrease the amount of product and make more reactant. If we decrease the amount of heat, then the reaction will shift to the right and make more products. This is why it's very difficult to light a fire in the desert during the daytime. The wood has too much heat. The air has too much heat in it, too much energy, and it's very difficult to light the wood on fire because it doesn't want to produce more fire, more heat. However, at night, when it's very cold, it's super easy to light a fire. And in the winter, it's super easy to light a fire because the amount of energy on the product side is very low, and so therefore it wants to shift to the products to make more heat. If the reaction is endothermic, then we're going to treat it like a reactant. Our reactant is on the left-hand side now. So we're going to treat it just like a changing concentration of a reactant. So if you think about an endothermic reaction, like putting an ice cube in your hand, if you increase the heat of your hand, the ice cube will melt faster and you'll produce more liquid water. If you decrease the amount of heat in your hand, so if you get your hands cold and then put the ice cube in it, you will decrease the amount of melting that will occur because cold does not help things melt. So, and again, if the reaction is exothermic, heat is going to be on the product side. If it's endothermic, your heat is going to be on the reactant side. How can you find this? Remember to look for negative for exothermic, positive for endothermic.